Hello, everybody. This video is going to cover question number 4 from the 2014 AP exam. What they've given us is a table of values for the time and the velocity of a train that's running back and forth on an east-west section of railroad track. So the first part is asking us to find the average acceleration of this train over the given interval. And so what I notice is they want average acceleration and they have an over a time interval. That tells me they're looking for the average rate of change, which for us, we just know is our regular old slope. So I'm going to go ahead and take the slope. I've got the velocity of train A at time 8 minus the velocity of train A at time 2 all over 8 minus 2. And I'm just going to get those values from the table. So at 8, I've got negative 120. The velocity at time 2 is 100 all over 6. So I get negative 220 over 6, which is negative 110 over 3. And then because this is a slope, I know my units for velocity are meters per minute. So I'm going to put that maybe to the side here. So this is meters per minute, and it's all over minutes. So then the units for my answer here are going to be meters per minute squared, or meters per minute per minute. And that would be the answer here. For that one, that was given 1 point for the answer with units for that year's exam. For question or part B, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t? So what they're asking us here is, can we guarantee that this function, the velocity function, takes on the value negative 100? Hopefully that triggers in your mind. What they're asking us is a question about the IVT, intermediate value theorem. So can you guarantee that a function takes on a particular value? Now, before I get started with the actual work, I just want to make a couple notes. So conditions for IVT, the first thing we have to address is our function, velocity of train A, is that continuous? We know continuity on an interval is a condition of the IVT. The second thing we would need to show is negative 100 between the function values of our endpoints? So between v sub a of 5 and v sub a of 8. So if we can show those two things, then we can say that the IVT applies and we can guarantee that the function will take on that value. So now we've got to go back to the problem and see what we know. So for the first part, is it continuous? If I look back here, they didn't tell me that the function is continuous, but they did tell me that this function is differentiable. So now I know if a function is differentiable, it has to be continuous. So for my first condition, I'm just going to write, since v sub a of t is differentiable, let me put, since my function is differentiable, it is also continuous. So we've addressed that first condition. Now we have to check, is negative 100 in between these function values? So if I look, let's see, I've got at 5, my function value is 40. At 8, it's negative 120. And I can see that negative 100 will fit in between there. So I'm going to write, let's see, 8 was my negative value. So I know that v sub a of 8, that was less than negative 100. And that's less than v sub 8 or sub a of 5 at time 5. So I've addressed here, I know the value I'm trying to prove is in between those endpoints. So I've met my two conditions, so now I just need to write my conclusion. So since I have these two conditions, I can say therefore, and I have to state the theorem. So by IVT, by the intermediate value theorem. And then for my conclusion, I'm just going to use the wording of my question to help me out. So we were trying to prove sometime t. So I'm going to say by IVT, there exists a time t in my interval from 5 to 8. And then I could say such that the velocity of train A at that time is equal to negative 100. And then we'd be done. We've proven the conditions and we stated the conclusion. So let's see. In this problem, they gave, I believe, 1 point here for the conditions, and then 1 point for the conclusion. And again, you have to state that that's by the IVT. Okay. For part C, let's see what they're asking here. At time t equals 2, train A's position is 300 meters east of the origin station. So east, I'm going to interpret as a positive number there. And the train is moving to the east, so it's moving in that same direction. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. So I need to know the position of the train at some future time. So what I need to know here, I'm going to use S of t for position. And just to be consistent, I'll use that sub A. So position of train A. So what I know, that position, and I'm trying to find it at time 12, that has to be equal to its starting position or its initial position. And then I need to know its displacement, which, if you'll remember, right, displacement is just the change in position. So in other words, if I want to know where that train's at, I have to know where it started and how much further it went. So let's see what we know. We know that at time t equals 2, the position was 300 meters. So I know this initial, or our starting, was 300. Now displacement, hopefully you remember, is just the integral of velocity. Displacement is what we get when we integrate velocity. I should have said. Now, to find out my bounds, here's where we have to be really careful. Since my position 300 was at time t equals 2, that has to be the lower bound of my integral. That lower bound has to match that time. And then since I want to know how far it got till 12, my upper bound would be 12. So there we have an expression with an integral, which is what they asked. Write an expression involving an integral that gives the position of the train. So that's part 1, was just giving that expression. Then it says to use a trapezoidal sum with 3 subintervals indicated by the table to approximate that position. So now what I need to do is actually use the trapezoidal approximation to approximate this value. So let's see what we have here. From 2 to 12. Now, that means, right, I don't have to include the interval from 0 to 2. I'm just looking at the interval from 2 to 5, from 5 to 8, and from 8 to 12. And trapezoidal means I do need to consider both endpoints. So at 2, it's 100, 5 is 40. 8 is negative 120. And then at 12, I have negative 150. So I know now that the integral from 2 to 12 of my velocity. It's approximately, what do we have? Trapezoidal is our base, 3 over 2, or our height, excuse me, 3 over 2 times 100 plus 40 plus, this again is 3 over 2. Now I have 40 plus a negative 120, which is minus 80. And then plus 4 over 2. And then I have negative 120 plus a negative 150, so negative 270, if I did that right. And then I'm going to go to my calculator here. And I get negative 450 here. So now what we've got is an approximation for our integral here. So now if I want to find that actual position, and I apologize that I'm running out of room here, I would say my position of train A at time 12 is approximately, and I'm just saying approximately because we approximated that integral, 300 plus a negative 450. So we get negative 150, and our distance is measured in meters. So what we would say is, now we kind of have to account for that negative. All that means is that that train is to the west of that origin station. So I'm going to put a little note here at time t equals 12. Train A is approximately 150 meters west of the station. Okay, so then for points, let's see. They gave a point for this expression here, writing the integral expression for the position. And then it looks like a point here for knowing that it was 150 meters west of the station. All right, last part. It gives us a second train, which is train B, traveling north from the origin station. It gives us the velocity of that train B, a function for the velocity. And then some at time t equals 2 tells us where the train is relative to that station. So find the rate in meters per minute at which the distance between train A and train B is changing. All right, so here, again, in terms of keywords, they want the rate at which the distance between the trains is changing at this time. So hopefully by now we're getting good at recognizing these related rates. So the first thing I'm going to do here to make myself real clear on what's going on is draw a picture. So I have two trains. I know I have origin station. I'm going to call that O. I have my train A that I know was moving east, and now I've got a train B that was traveling north. So I'm just going to put arrows to show that direction. So I'm going to call this side A, side B, and what I want to know is how this distance between them is changing. I'm going to call that C. So the first thing I need, nothing is constant here because both of those trains are in motion. So I need a formula that's going to relate A, B, and C. And since this is a right triangle here, we have A squared plus B squared equals C squared. So now I need to differentiate this with respect to time. So I'm going to get 2A times dA dt plus 2B times dB dt equals 2C times dC dt. And to simplify things a little bit, I'm going to just factor and cancel. Since all the terms have a 2, I'm just going to get rid of those so I make my numbers a little smaller. They're big enough as it is. So now I've got 6 quantities that I'm concerned with. I've got A, B, and C. I've got dA dt, dB dt and dC dt. So let's see what we know. At this time 2, it's telling us that train B is 400 meters north of the station. So at time 2, I know this is 400. Let's see. They're also telling us, they gave us the formula for velocity here. So that means I can plug in 2 for t to get that velocity. So I'm going to do that really quickly. Oops. 25. And it looks like I get 125. Again, that came from plugging in 2 into the velocity function for train B. So I got 125. Now I have to go back and look at what's going on with train A. They told us here that at time 2, which is the time we're looking at, train A's position was 300 meters east of the station. So this is 300. And then I need to know how fast that train was moving. Well, I can look back at the table at time 2. It's telling me the velocity of train A was 100. So I can put that here. Now, let's see. They want to know the rate at which the distance between the two trains is changing. So my dC dt is going to be my unknown, which means I need to figure out at time 2 what is the value of C. Well, hopefully we recognize, since this is a right triangle, we have a 3, 4, 5 triangle, so C is going to be 500. So now everything's good. I only have one unknown, and so I can go ahead and plug in and solve. So I get 300 times 100 plus 400 times 125 equals 500 times our unknown dC dt. So if I go ahead and solve that, I would ask you guys to verify this in your calculators, but you should get 160, and then our units are meters per minute. So the distance is increasing at that rate. All right, so then in terms of points, we get 2 points here for the equation relating all the variables, and then you get a point here for your answer with units. So that one was kind of a lot. Please make sure you reach out if you still have questions about anything that was going on in that problem. All right, thanks.